Thank you to Magnimind for organizing this, and thank you for coming and listening to me. I'm here to talk about the rise of immediate intelligence. This is, well, we'll get into the details of what we mean by immediate intelligence, but it's focused around the Apache Druid database and its capabilities to deliver real-time analytics. So let me jump right in. We'll talk about the data temperature spectrum. So we're going to create a contrast between hot and cold data, hot and cold analytics, to define it first. Then we'll go through the database evolution in dealing with analytics. So what's happened over the last 40 years or so in terms of analytics. And then we'll go into the Druid story, how Apache Druid came about and how it became an open source project. And then we'll dig in, open the hood a bit and figure out how it works, how it delivers this immediate intelligence capability. And I'll leave you at the end with a few more resources to learn more about Apache Druid. So with that, let me get started with the temperature spectrum. So like I said, we're trying to create a contrast between hot and cold, right? So therefore the two images. Starting with the cold side of analytics, this is the realm of data analysts typically, right? This is environments where they have either a data lake or data warehouse where they know the data really well. They know their data models. These are people who typically know how to write SQL. They may use visualization tools to generate new analytics that are useful for the business. But they're usually strategic in nature, and they usually don't work on immediate new data, but on some less fresh data. The best cases are typically daily batches that are adding data to the environment. So you're looking always at a little bit in the past. And in these environments, slow queries, nobody likes slow queries. Everybody wants it to answer quickly. But in these environments, shooting out an analytic that's going to produce some kind of strategic report could take minutes, and it's okay, right? It's not, it doesn't need to respond immediately. In contrast, what we mean by hot is response times are very quick, right? We're talking about serving application interfaces, user interfaces that require sub-second response times in order to keep the user engaged. They're usually on fresh data, and this means on streaming data, so on very recent events, or understanding what's happening now in the context of what was happening further in the past. So it's about combining fresh data and more historic data. These environments are also typically have much higher concurrency than typical analytic environments. So we're talking, instead of tens or hundreds of users, we're talking about thousands, even millions of users in some cases. And the reason to have such fast response times is to provide high interactivity, right? So it creates an experience that's interactive for the user rather than shoot a report and go get some coffee. It's click and produce a result, and then based on the result, click on something else or filter in a different way, or do the next question immediately, and therefore allows you to have this ability to have a conversation with the data. So that's the contrast we're creating between hot and cold analytics. To summarize a bit, to compare between traditional business intelligence and business and immediate intelligence. And the immediate intelligence side, we're focused on speed. We're focused on democratizing the data and socializing the data. So people in this environment share their results with each other, and that makes the environment grow. It's an environment where people can explore the data. It's not just about the fixed reports. So this kind of interactive capability with analytics provides this personalized decision making, right? Rather than strategic decision making. It's more about making decisions to act on immediately, or potentially to investigate further immediately. So it's not just about access to the latest data, the most recent events. It's also about taking the most recent data, understanding how it compares to relevant periods in the past. So it's about analyzing the now and the past to provide context. So use cases. There are many use cases out there in the wild using Apache Druid at this point, but this is a sampling of them. In the risk and fraud space, we see this is about fast-moving transactions, right? This is an example of credit card transactions. There's lots of them, and you need to be able to evaluate them quickly to determine whether this could be fraud or not fraud. In order to do this, it takes things like individual spending profiles or recent spending profiles and the comparison to that current transaction in order to come up with some indicator of whether it's potentially fraudulent or not. So it needs quick analytic responses, and it's a very high volume environment. So that, again, we're talking about high data volumes, high concurrency, and fast response times. In the data-driven application space, we're talking about websites or mobile apps. Here, typically, and these are analytic apps, right? This is some kind of mobile or website application that has an analytic component to it. They have concurrency that's off the charts, right? If you have a successful mobile application or successful website, you're typically going to have thousands up to millions of users, and therefore concurrency is very high. And because these applications are customer and consumer facing, the reliability and speed of that response is paramount, right? It's what defines the customer experience. So that's another important use case. In network performance, so this is about understanding and providing service reliability and security, right? So it needs very fresh data. The data is the paths that individual data packets take. So it's the traffic patterns across networking infrastructure. So there's tons of data. This is a very high volume data use case, such that people and machines can query it and detect odd traffic patterns in the case of security, or potentially failing infrastructure, such that it can be addressed quickly to provide the reliability and security that is expected of it. In clickstream analysis, it's about understanding journeys, right? It's about understanding who clicked on what, and then what else they clicked on, and what else they clicked on after that. So it's about understanding how they navigated a particular application. So in this space, there's clicks, all the clicks are events, and therefore it's a lot of data and very high concurrency as well. And it's about understanding the differences in activities between different groups of people and trying to classify them, trying to create segmentations and do A/B testing to understand and optimize the user experience, and potentially with the real-time analytics drive their experience, customize their experience based on what you know about them and what they're doing now. The other use cases, I'm not going to go into all of them, but the digital ads one is an interesting one that that's where Druid was born. So we'll talk about that in a bit more detail in the slides to come. By the way, stop me at any time if you have questions. Raise your hand. I think I see it, and I see the chat. So ask questions at any point if you have any questions. Otherwise, I'll just keep moving. So we've talked about, we create this contrast between hot and cold analytics. So let's take a look at the history of databases and how we've been dealing with analytics and how that has caused, hotter or colder experiences for the end users. So we started back when I started programming, which was a long time ago, building applications that were transactional applications, right? We took relational databases like Informix or Oracle or SQL Server and built applications that automated operational processes in a business. And because of that, we recorded transactions, we recorded workflows, we managed that, and that generated information, events. Somebody put in an order, somebody fulfilled the order, somebody put in a PO, et cetera, right? So all of these that became, the ERPs of the world, started generating lots of data that became interesting to the business in terms of analytics. So at the time, what seemed the simple approach was, okay, so we'll just add more queries and add some reports to the application to build an analytic component to these applications. Now that created a conflict of resources, right? Because now we had to operate the business and we had to analyze the business. And the analytics tended to, want to read all of or large portions of the data and build out these reports. So it consumed resources, a significant amount of resources. In many cases, it was a roadblock for or conflicted with the ability to operate the business. So at the time, they won't call it data engineers at the time, architects, system architects at the time, came up with this idea of the data warehouse, right? And the main idea here, let's separate the workloads, right? Let's take all of the transactional data that these applications are generating and put them in a separate database that's a special purpose database for analytics. These were typically MPP architectures or massive parallel architectures like Teradata, like Netezza, that provided the ability to analyze large amounts of data. And because it was on a separate system, now we'd segregated the workloads, right? We have the transactional workload doing its thing, giving us data on a batch basis to do analytics on in the data warehouse. Now, these environments weren't, it helped that conflict between the resources, but also created a different kind of problem, right? And that problem is called ETL. This is the idea of extraction, transformation, and loading data from many sources into a data warehouse. And so building this required design, development, and maintenance of data models. It required people to spend time analyzing the data sources, understanding the business processes so that they could model the business appropriately, profiling and cleansing the data, delivering this highly structured data model designed for these analytics. That creates a time lag between the creation of the sorry about the dogs, the creation of a requirement for a new analytic and the time that it could be built, because you had to do the analysis of the sources, bring in the data, see if the data was already in the data warehouse or not, bring in new data, and finally create these new analytics. So it was kind of a cold experience from that perspective, right? It took time to build these things. And even once they were built, you needed the data analyst to generate new reports. So we started seeing another set of databases appear, this idea of OLAP databases along with visualization tools like Qlik or Cognos that allow the end user to access a subset of the data that that's my dog, sorry. So they create a subset of the data that was aggregated in some form to produce some subset of analytics. So we have things like sales data marts or marketing data marts or business departments specific data marts that were a subset of the data that were created to produce a subset of analytics, but with the visualization tools, it gave the end user a hotter experience in terms of I need to answer a new question. They could just go in, change some filters, change some groupings, and build the analytic that they needed to build. So it helped in terms of making it a little hotter, but there's still significant latency between the data source and and these data marts. I'm seeing which animation I'm on here. Well, there was also, because these things were so successful, we also saw the appearance of a rogue data marts. These were ones that were, users didn't want to wait for the time it took to build the new data set inside the data warehouse. So they went directly to the source, built their own, and these things became a bit of a headache for IT departments. But anyway, this was a successful approach at the time. It created a better experience, but it's still not the immediate intelligence we're talking about, right? The next thing that happened is big data happened, right? We started seeing on the transactional side, we started seeing sharding of the data. So we're separating the data into different subsets, whether it was, by customer, by region, by store, whatever sharding of the data was needed and of the workloads in order to deal just with the transactional workload that was also growing. So we saw things like Mongo and Cassandra and Couchbase deliver on that, or solve the problem of scale on the transactional side. Along the same time, we also saw the appearance of a data lake. The data lake's idea, or basic idea, is that instead of trying to create the data warehouse where we're thinking about how to model everything and how to transform all the source data to produce that description of the business that was a single version of the truth in the data warehouse, the data lake took a different approach. It said, well, why don't we just put all of the data as is from the transactional systems into this space where anybody can query it. And we saw, therefore, the appearance of distributed and scalable query engines. Now, these one of the things to note here is it's not that the ETL disappeared. It's that it sort of became a different thing, and this we said ELT here, in that it was extracted and loaded into the data lake, but the transformation side still needed that specialized knowledge. Somebody needs to know what the data structures are for each of those data sets that's being put into the data lake in order to take advantage of them. So this expertise in the data analyst is still something that's needed in this kind of solution. Now, don't get me wrong, things like Hive and Trino solve this scale problem on the analytics side. So now we'd solved the scale problem on the transactional side, we solved the scale problem on the analytics side, but the experience is still not on fresh data, right? We're still talking about batches here that are moving into the data lake and then being, quite these distributed query engines gave the ability to query almost any data that's in the data lake. So that was actually quite useful, but still not providing this immediate intelligence capability that we're talking about. To make matters a little worse, we started seeing a lot more data, right? From websites, from IoT devices. We started seeing data streaming through streaming technologies, even transformed data within the streaming technologies. But having that all arrive in the data lake still created this batch latency to the end users for the ability to see things in real time. So this is where a serving database comes in. And this is where Apache Druid fits in. A serving database is different than a distributed query engine in that it stores a copy of the data, but it stores a copy of the data in some optimized form. Right? We saw implementations of this using things like Cassandra and HBase, where calculations were created ahead of time, right? So some combination of analytic was created, and those were stored in key value stores, so it made those particular analytics very quickly accessible, and therefore being able to drive this kind of more real-time experience in the end users. So this is where Apache Druid fits. It fits in this space of a serving database. But Apache Druid is different. It's not a key value store. It actually stores, well, its objective, right, when it was created was to provide the best serving layer that we could possibly think of, right? And that meant a few things. It meant dealing with very high concurrency. It meant delivering very low latency queries at very high data volumes with a lot of flexibility in terms of how you could slice and dice the data. So like I said, Druid is not a key value store. Instead, it's a column-oriented data store. It's similar to the columnar stores that you might see in some data warehouses, like the Parquet and the ORC formats, but it's not. It's a different. It's a format of its own because it uses some other elements that make it interesting that we'll get into a lot more detail in a bit. But so it's columnar. It's all of the dimension columns are all pre-indexed. It allows for streaming ingestion and batch loads from data lakes at the same time. And it does the resource management to provide real high availability and distributed distributed compute that enables this fast response times that we're talking about. And Druid not only did the data lake sourcing or other source of data in batch form, it also has the ability to directly consume from streaming data. So it gives you the ability to both query the now, what's happening as the events occur, as well as the historic data that it's preloaded from, potentially from a data lake, or from the history it's built from streaming. So that's sort of the history of databases and how we got to where Apache Druid fits and what the space it's actually trying to address, the space of immediate intelligence. So let's go a little bit into the Druid story. So like I said, it starts back in 2012 in the ad tech industry. In the ad tech industry is about a bunch of publishers with content that have spaces for ads, and advertisers trying to place their ads in the most efficient way possible, right? And understanding what their impressions are and what their click rates are on different segments of the publishing spaces. So this company wanted to build something new. There was a lot of existing competition in this space, with companies providing a lot of analytics about the different publishers, but nobody was doing anything that combined this real time with this historic analysis and provided an experience that was immediate intelligence. So what they wanted to build was this. Right? They wanted to build these applications that would have this kind of response time. One of the things I like, so what you're seeing here is videos of Imply Pivot. This is a visualization tool that Imply produces that uses Apache Druid as its database to drive this kind of response times. What you're seeing is, users in real time, this is not accelerated, users dragging like dimensions into the visualization layer, and that produces queries to the database, and it responds with that speed, right? So this is what we mean by an interactive experience, by having a conversation with the data, because it allows you to very quickly navigate the data and find insights within the data. So they tried sort of the whole history, right, of databases that we just went through. They tried relational databases, they tried data lakes, they tried warehouses, search engines, time series databases, and they all had problems in delivering this real-time experience. They had, they were unscalable or very expensive to scale in some cases, disjointed. The data was, the historic data from the streaming data had to be queried separately. So it was limiting and it was slow, and therefore it wasn't capable. None of these solutions were capable of producing the real-time experience that they were looking to produce. So as companies in Silicon Valley tend to do, they decided to build their own. So they built a new database, and that was Apache Druid. The requirements were high performance, so this meant low latency distributed query execution with very high throughput ingestion, scalable ingestion. It needed to be real time, so we need to be able to query real event data as the events were occurring with very, very low latency from the occurrence of an event to the actual, to it being queryable in an analytic. It had to have broad analytic capabilities with statistics and ranking and counts, and it had to be a database, right? It had to be very highly available, time sharded, partitioned. In this case, the decision to make it to make the analytics so versatile was to use columnar and pre-indexed compressed forms that would enable this fast query capabilities. So they took what they learned, the group of engineers took what they learned from the experience of other databases, what they learned from log search databases, where they took the real-time ingest and the flexible schema capabilities from time series databases. They took the low latency ingest from event to queryable very fast, along with this idea of time-based storage, so segmenting the data in different time intervals, as well as the ability to use time functions to reaggregate at different granularities of time. from columnar databases, the efficient storage format, as well as the ability to do these fast analytic queries and provide data distribution in a clustered environment. So with all this, they built Druid, and it works. It's a database that's been proven to do many millions of events per second of ingestion. It's a query engine that gives aggregate results at sub-second speeds over that data. And it's a storage system that is both storage and compute efficient, right? So you can give this unified view of real-time and historical data in one place. So with all this, they built a successful real-time interactive application, and the business actually got acquired. But along the way, while they were building this database, they decided to open source it, and they created the Apache Druid project. And you can read if you go to the Apache Druid website, you can find the original paper that they wrote that describes the problem that they were trying to solve and the architecture that they decided to use to solve it. Once it was open sourced, very quickly we had one of the first adopters was Netflix in 2013, just months after being open sourced. Along with them came big names in big data like eBay, Yahoo, Cisco, and PayPal. And these became part of the original PMC for the group in the first project committee meeting in 2015. This snowballed, and we got use cases all over the place of companies that use a lot of data, that have a lot of users, and require this immediate intelligence capability. They all recognize this as a special, different use case to traditional BI, and started using Apache Druid for this to do things like video streaming analytics, infrastructure monitoring, clickstream analytics, API health monitoring, and so forth. And all working together in a community in the Apache Druid project. So if there aren't, let me check if there are any questions. Surprised to hear technologies that aren't location-based companies. You mean like geolocated data? Is that the question? Oh, like cars. Yeah, I mean, if you have a use case for tracking cars or something like that in real time, that does sound like something Druid could tackle. I don't know that there is that yet, but anyway, that is interesting. So let's dig in a little bit onto how it works. So I'm just placing it again. Remember, it's a serving database. It's meant to drive applications that require this kind of interactive response times on some set or some subset of the overall data available in the data lake that's geared toward a particular function that where this fast analytics for decision making is interesting. So what's the architecture? The architecture is, so this is a view of the architecture. Let me start by describing the three major processes that this architecture is trying to solve, right? One is data ingestion, right? And we have the ability to do, if we start on the right there, to do both streaming and batch data, and both are highly scalable. They scale with the data server. So each of these data servers have a historical component and an indexer component. The indexers are the ones that are doing the ingestion, whether it's in batch or real time. And they're fully scalable, right? So you can create as many indexers as you want across as many nodes as you want to increase the ingestion capability. And in streaming, that aligns with things like partitioning in Kafka that allow you to also scale the throughput of messages. So from that perspective, it increases this. It's really, we haven't seen a limit to the scalability of it. The biggest one is doing, I think it's 10 million events per second is the high water mark that we've tested. But this ingestion capability is fully scalable from small to very, very large. And the ingestion, these indexers are taking in the data from streaming technology like Kafka Kinesis, and that's built in to Druid. And these indexers build these segment files. These are the columnar formats, the index format that we talked about. But while they do so, they're keeping the real-time data in memory, so it can be queried. And we'll get back to query in a second. So they build these segments and push them. We see them pushing them down, these little yellow squares in the diagram, pushing them down to something called deep storage. This is distributed storage, right? This is HDFS or this is S3, any kind of object store that is distributed and highly resilient in nature. So the ingested data is built into these optimized segments and pushed into deep storage. And then that's where the data distribution process comes in. So the master servers are in charge not just of what ingestion is going on and handling the tasks delivered across the cluster for the ingestion, but also for data distribution. And that is understanding which data segments have been built and are published and are ready to be distributed across all of the data servers in the historical processes. So there's a prefetch process that the coordinator tells the historicals to do. It tells which historicals, which segments to get, and it distributes all the segments across the cluster, creating replicas wherever you ask for replicas, which provide high, resiliency, high availability in the case of the loss of a data server. So it's very highly available from that perspective. And it also delivers distributed compute. So each of these or subsets of these data segments are assigned to each of the historicals, and each of these historicals respond to queries as well. So we've talked about two things that respond to queries, right? We've talked about the indexer that's receiving data in memory, responding to queries, and the historicals that are taking, they're prefetching data segments from deep storage to respond to queries as well. So let's talk about queries. So as users submit queries either in, there's a native JSON format to define queries, and there's also SQL to define queries that are submitted to the brokers, and the brokers themselves are also scalable. So you submit the query there, the broker has the metadata to know which indexers are dealing with which real-time segments, so which data is being ingested, for what period of time is being ingested in real time and is therefore in memory, and which data is already in the historicals and is therefore considered historical data and can be queried there. So with that information, the broker fans out requests to the data servers that have pieces of data that are interesting for, or that are needed for that particular query. And each of the historicals responds to their historical portion of the query, and each of the indexers respond to the real-time element of the query from the data that it has in memory. So in that way, we combine both the real-time data that's inbound as of now, and the historical data that's already been put into segments and distributed across historicals. I know that's a lot. Any questions there before I move on? I don't see any. So what I'm going to dig in. Oh, thank you. I'm glad you found it good. So let's dig into those little yellow squares, right? And what the data format is in each of those. We take advantage of 4 different strategies in creating these files. First, the data itself is compressed, and we'll take a look at how it's compressed in a second. All of the dimension columns have secondary indexes, and this isn't something you need to build. It's just always there. They will always be indexed, and we use dictionaries to sort and categorize the distinct values in each of the columns, and you'll see how those are used in query. And finally, we use this idea of latent materialization. This means resolving the queries as much as possible in their encoded, their compressed form, which is more efficient in terms of compute, and only at the very end converting those encoded values into their original values, which tend to be bigger for the most part, in order to produce the final results for the end user. So let's dig in a little further into how this works. This is an example of 8 rows within a small data set, just to illustrate how this works. Typically, you'll see data segments that have millions. Actually, the recommended target for the size of each of the segments is about 5 million rows per segment. So inside of each of these segment files, you'll find a time column, because it is a time sharded database. All the data is split into time segments. So each segment file contains a particular interval of time. And within the data itself, you'll see that each of the rows has a timestamp associated to it, reflecting the timestamp of the event that you're modeling here. Then you have dimension columns. In this case, we have just artist and city. We're describing here, events, purchase events for music venues. So we see the artist column is divided into 3 things. The data that you see in encoded form, so you see numbers 0, 1, 2 in this case. And then you see the dictionary, which actually translates those numbers into their original values. The dictionary is the distinct list of values for that particular column within the data set that was processed to build this segment. And it translates original value AC/DC is 0, Kylie is 1, and Silverchair is 2. So the encoded form is clearly smaller because it just has a number for each of them, and it's also much more it's compressible, right? So we compress it beyond that using I'm not sure what the algorithm of compression we use, but we compress it further. And we have an index associated to each of these columns. What the index gives us is, if you look at those 3 example rows, it gives us 2 forms of indexing. One is just the list, and that's the first thing in brackets, is the list of rows that have this value. So what we're seeing in the index in position 1 is for the value of the dictionary in position 1. So AC/DC appears in rows 0, 1, and 2. Beside it, you see a bitmap, right? A bit field, and that's called a roaring bitmap index. And the way that works is each bit within the bitmap represents a row. And if it's turned on, it means this value is present in the row. If it's 0 or turned off, the value is not present in that row. So we see that 0, 1, and 2 correspond to that bit field. The first 3 elements are 1s and the rest are 0s. Now, this becomes really interesting when you're querying across multiple dimensions. So you're filtering on multiple dimensions. Because, if you're filtering on one dimension, then, we could see if you're looking for Kylie, for example, we can go to row 2 of because we found that in the second element of the dictionary. We go to the second element of the index, and that tells us that we only need to look at rows 3 and 4. So that's all the information we need if we just had one filter. But if we have 2 filters, we can then say maybe it's Kylie and Melbourne. I don't know if those 2 have intersections, but let's see. And you take the bitmaps and do bitwise operations on them. You do ands on them or ors on them to resolve a more complex where clause with bitwise operations with the roaring bitmaps. And that gives you a very quick operation, very quick result as to which rows you need to look at for that particular query. So filtering is very optimized in this environment. And so city is the same. It's a dimension column, and it's encoded in the same way as artist. And then you have the measures. These are things like price and like count that are measures that you're going to run statistics on, and that you're going to need to analyze across all of these other dimensions. So let's see how a query is resolved with this format. So this is a simple query that's looking to look at the total sales by city for a given artist, in this case, AC/DC. So how would this data structure help speed this up? The first thing that would happen is because the where clause has the artist column, we'd take a look at the artist column in the columnar format and just read the dictionary, because it's a sorted dictionary, it's going to be an extremely quick search, even if it's not the first position in the list, to find that value, right? And so once we find that, we can go directly to the index to find that same position with the index, or maybe there's multiple, if there's multiple values, there's multiple positions and things of that nature. But anyway, this helps us find that we only need to look at rows 0, 1, and 2 in this case. Since there's no other combined filter here, that tells us the rows we need to look at within this segment, so we can move on. And we only need to access the column, the other columns that are involved in the query. In this case, we're looking for city and price. So at this point, we can only access from those columns. We know we only need to access the first 3 rows. So we access those first 3 values of the city column, and we access those first 3 values of the price column. And at this point, we have enough information to build the aggregate that we're looking for, right? So we can group the first and the third row for city equal to 2, and the second row for city equal to 1, and do the sums on price on those things. And once we've done that, we can then do late materialization, which is translating the 2 and the 1 that were in values of the city back into their original values and produce the final result. So I guess one of the key points to say here is, if you notice, we did not scan the file, right? We didn't scan any of the columns in the file. As long as there's some kind of filtering in here, because we have indexes across all of the dimensions, we can quickly find the rows that are relevant and do the calculations very efficiently from this perspective. So this is what drives the speed, this and the fact that we're distributing this. So let's go back to the architecture. Now that you know what those files are present and distributed across a cluster that can be almost of any size, and therefore deal with that speed with large volumes of data, even if you're spanning multiple timeframes, because the data is distributed across the cluster and will have all of that compute addressing multiple queries. Because it's so efficient at driving, at resolving these queries, we can drive much higher concurrency, because we're using very limited resources to solve each of the queries. So I'll stop there and see if there are any questions before I move on, because I know that's also a lot. Okay, I don't see anything going. So I'll move on. With Apache Druid, we see implementations of many different, I showed you an example of a front end of a visualization tool that's put in front of Druid, but there are Apache Druid implementations out there using many different visualization layers like Grafana, Looker, Tableau, or Superset. There are companies building their own, right? Building custom applications, because Apache Druid can be accessed either directly through its REST API, so through HTTP calls, or through JDBC. You can build on almost any tool. We have practitioners out there doing things in Elixir and .NET and React and Angular, and this is just to name a few. And we've also seen this in this particularly interesting for this group in the machine learning space, right? Because we see people using Druid in 2 different forms to help or to enhance the analytics. In one form, you have analytics or machine learning models applied in the pipeline, so in the streaming pipeline that's delivering data to Druid, such that those analytics, maybe it's things like propensity for this transaction to be fraudulent or not, added to the data as it's coming into Druid, and therefore making it available for analytics, for slicing and dicing analytics for the users. Another form that we've seen is where people are using Druid to deliver fast aggregations across different dimensions to produce input into machine learning models in real time. We've talked about the data temperature and what hot and cold is. We went through the database history and sort of learn how that's evolved over time and where Druid fits. We talked about the Druid story. we dug in a little bit into how it works. So I'll just leave you, because I know it's a lot. I just saw the message. I'll leave you with some more resources. And you can reach out to me as much as I'll leave you my email here in a second. If you have any other questions, I'll gladly respond to those. I see a question. If the Apache Druid stores a copy, is it good with concurrency? Is it a functional programmer's choice? I'm not sure whether the functional programming aspect of it is necessarily relevant, but yes, it does store a copy, right? It's storing an optimized copy of some subset of data with some purpose in mind, right? So this, remember, we're driving applications. So it's really about what the end user application needs. In terms of fast moving data and fast analytics, that's really what drives the use of Apache Druid. Whether that's done with functional programming or some other form of programming, that's I think a different subject. I'll leave you with a few more things. There's a large list of use cases. These are so in the Apache Druid website. That's druid.apache.org, where you can find a large list of use cases. These are the community members that have described their own use case. There's links to videos. There's a bunch of videos on YouTube on how, for example, Netflix has videos from their last Druid Summit, and many more have videos about what they've done with the technology and how they've implemented the technology, and what challenges they ran into and how they solved those. So those are all interesting reads. There's the Druid Forum. This is druidforum.org. This is a Q&A environment, right, where the whole community participates, both in asking and answering questions. There's articles there, blog posts about implementation use cases, implementation techniques. So that's very useful. There's the Apache Druid website itself, where you can download. Again, it's open source, so you can download the software and deploy it and use it yourself and test it out. There's tons of documentation there about how it works and how to use it. There's also the GitHub project. So again, it's an open source project, and this is where we like to invite everybody, right? So if you're a Java developer, or even if you're just a user of the database, we love more people participating in the community. This is what drives the project, right? So either by committing new features and new code, or even by reporting issues to help us improve the quality of the product, or even improvements to the documentation, are things that the community helps with, and in order to evolve this project. And the GitHub page is where all that is done. There's blog posts in our website. So we have our company blogs, engineering blogs from our engineering team, describing what's going on with Druid, and community blog, where we publish use cases and implementation strategies or implementation walkthroughs from our community. There's some free training if anybody is interested. Right now, it's free. These are actually two very good hands-on training courses. There's the Apache Druid Basics and the Apache Druid Ingestion and Data Modeling courses out there. It's at learn.imply.io. Again, they're free right now, so take advantage of that. Jump in and learn a little bit more about Druid. And with that, I'll just leave you with this page, which is a bunch of different ways in which we communicate. You can communicate to us through email, like I said, through the forum, through meetups like this one. We're glad to participate in meetups. That's part of what we do as the community team to help grow the Apache Druid project. There's the Slack channel, the training I mentioned, and we have groups in LinkedIn and tags on Twitter that you can see tons of information about us. So I'll leave it there so you can take any of those, and I'll open it up for any more questions. me see if there's any other questions I didn't answer. I think I got them all.
Thank you, Sergio, for the talk. It's pretty good. So people can have this in YouTube, and we're gonna broadcast it tomorrow. I mean, we're gonna post it tomorrow. And I appreciate everyone's time. And thank you for Sergio for presenting today.
Thank you for having me.